Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. After the webinar is over, please take our survey to tell us how we've done. Throughout the presentation, you can network with others or submit questions to the speakers in the box next to the slides. Download resources from the folder icon. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Email Us. If you experience any technical issues today, please refresh your browser by hitting F5 for a PC or Command R for Macs, or email webinars@bmpmedia.com for one-on-one support. And now I'm excited to turn it over to today's moderator.
Good afternoon and welcome to this webinar, 40 is the new 20, Why Engineers are the New Guardians of Occupant Health. This event, brought to you by Engineered Systems, is sponsored by Nortec. I'm your moderator, Robert Beverly. I'm the editor of Engineered Systems. Thanks for joining us today. Today's presenters are Dr. Stephanie Taylor and Thomas Berger. Dr. Taylor graduated with honors from Harvard Medical School in 1984. She practiced clinical medicine and did academic research in cellular growth mechanisms for the next 20-plus years. During this time, she became very concerned about new infections that many hospital patients contracted while they were being treated for unrelated issues. Determined to better understand the connection to the hospital's built environment and airborne infections and to find a practical solution to ensure better patient health care, she obtained her master's degree in architecture from Norwich University. After several years working in an architecture firm focused on hospital design, she founded Taylor Healthcare Commissioning, Inc., the nationally recognized consulting company that specializes in designing, building, and maintaining hospitals and other commercial buildings for optimal patient health and occupant safety. Dr. Taylor continues to expand her work through ongoing studies and client assignments that allow her to better understand the relationship between the built environment and occupant health that result in the decrease of both acute and chronic diseases through management of indoor air quality and other building parameters. Tom Berger graduated from Oregon State University in 1982 with a BS in Mechanical Engineering. Starting his career with an air handler manufacturer, Pace, in 1984, Tom was able to develop practical knowledge in heat transfer, materials science, acoustics, vibration, airflow, and control, along with flow visualization and computational flow dynamics. Further research done at the Pace Labs was instrumental in developing some of the very first, quote, clean air handlers to be used in the making of microcircuits. Tom was awarded a patent in 1996 for a simple airflow measuring device that has no impedance, is highly accurate, and costs almost nothing. Virtually every fan manufacturer in the world now uses that device. In 2000, Tom left Pace as Vice President of Engineering and joined the sales team at Applied Systems Northwest. He has continued to increase his knowledge of the HVAC world with challenging projects in creating ideal environments for everything from lithium-ion batteries to seed archives to surgery suites, always with an eye toward moist air as the point of expertise. Now, don't forget to submit your questions also, and later in the program, our presenters will address as many of those as possible. And also, today's event is being recorded and archived at our website. That's esmagazine.com. With the housekeeping done, now I'm excited to turn it over to today's first presenter, Dr. Stephanie Taylor.
Hello, everyone. This is Dr. Stephanie Taylor, and I'm going to go on a first-name basis. So now you know a lot about us, and I wish I could see all the bios of people who might be attending, but I can't. But feel free to communicate by email after this, and we can get to know each other better. So why are engineers the new guardians of occupant health? Well, the reason is that as a physician, I can say that medicine is kind of in a difficult place right now. And I think by the end of this webinar, you'll have a better sense of why building managers, engineers need to help with this problem. So today, let's first talk about some health trends, disease trends, and how that might relate to building ventilation. And then let's talk about air hydration, which is another word for indoor humidification, but it designates a very specific and healthy zone. And then we'll talk about the current climate, pun intended, around humidity. So getting started, we'll talk about health trends. So some alarming stuff is going on in our civilized and built environment. One, patients are dying from the experience of going into the hospital. And all of the listeners, I would ask you, although I can't hear you real time, how many of you have either gone into the hospital and gotten a new infection or know somebody who has? And unfortunately, I think more hands would probably go up than we would want. So that's a problem. Healthcare costs are out of sight. There's an increase in chronic diseases, especially allergic disorders and autoimmune diseases such as inflammatory bowel disease, lupus, multiple sclerosis, and then as well as metabolic disorders, which may or may not be related to inflammation. And fourth, there are many infectious diseases which are reemerging, cholera, tuberculosis, just to mention a couple. So it kind of begs the question, are we missing something, or why are these things going on? Whoops, wait a sec. Okay. This actual slide is actually out of order, so hang on. Bear with me. Okay, how do I get forward? Okay, so Ken Dickerman, who is the architect for all the VA hospitals, said, "We shape our buildings, then they kill us." Is that true? Because if it is, that's a really alarming idea. So with that alarming idea and alarming question, luckily, in 2017, if I can get the slide to advance, thankfully we have some new tools so we can begin to answer that question of whether or not the indoor environment is adversely affecting our health. And every time we have a new tool, we get a much broader perspective. For example, when the microscope was invented, we began to learn about germs and bacteria and how they might relate to disease. The telescope, we learned that we weren't the only people in the whole universe. And then now we have next generation sequencing tools or metagenomic tools. So we can actually look at the DNA fingerprint of organisms both in our body, on our body, in the built environment, in the air. So of all the listeners, think about if you've read about the gut microbiome or about next generation sequencing tools, because that's what I'm referring to by the Genoscope. So let's take a look at what we can't actually see with our bare eyes. Let me see here. I've got to get that video. So here is an animated video based on data. And as I'm speaking into the phone and everyone who's listening is breathing, these little droplets are coming out of our airways. They're about 100 microns in diameter. They're carrying whatever organisms are in our mouth. You know, normal bacteria, probably a few fungal organisms, maybe some virus if anyone's got a cold. So in this animation, you see an engineer or architect working on a CAD drawing, and she has skin flakes shedding from her arms, her face, her hair. You can see her intestines are illuminated because we have a lot of organisms in our digestive system that can come out into the air one way or another. You can see that skin flakes and particles that are in the air settle, and ones that are settled get resuspended. So hang on, I'm struggling here with technology. So we've learned from these tools that as human beings, we are only about 30% human. The rest of us is made up of microbial cells. And we knew this once we sequenced all the DNA from humans. So each of us is like a little ecosystem walking around with all of our bacteria and fungal organisms. And 99% of these are healthy. They help us with our digestion. They help us with our immune system. So if anyone's a germaphobe, don't like freak out right now and think that, you know, game over. If you think anything, just think that you don't really have to worry about these organisms so much. Sorry, somehow the slides got a little jumbled around. So as human beings in buildings, you can imagine that we send these organisms into the building, and the building containing organisms from previous occupants sends those microbes back to us. And on the bottom part of this slide, with the blue, magenta, and green colors, this group from Oregon showed that depending on how a building is ventilated, different organisms will prevail in a space. For example, the bathroom, which may have a different kind of exhaust fan, will harbor different organisms from, say, an office. So that depends on the ventilation, and it depends on the activities. So not only do humans send microbes into the building, and the building hangs on to those and allows growth of many of them, but how we manage that building is actually selecting. It's like another evolutionary force that selects for those organisms, which is a pretty interesting concept when you think about, if you think about the implications of ventilation on all of these microbes. So we also know that people who spend a lot of their time indoors, which is most of us, have a much less diverse species of organisms in and on us. So the microbiome, which is the word that we use for the organisms in the environment, the microbiome of people who spend time indoors is much more restricted when you compare it to people who, usually in different cultures, who spend a lot of their time outdoors. So you can see this picture of the cowboy next to the tree has many more types of organisms than the person indoors. So the same group that's done that study, Dr. Jessica Green's lab at the University of Oregon, also showed that depending on how you ventilate the building, you not only impact the diversity of organisms, but you also select for ones which are more or less closely related to microbes that cause disease, which we call pathogens. So on this graph, you can see on the x-axis you have the diversity of organisms, and on the y-axis you have how closely related those organisms are to pathogenic microbes. So for example, on the red dots on the upper left are narrow in diversity and high in pathogenicity. Those are the ones associated with mechanical ventilation. And as you move towards more outdoor air, you see that the organisms are more diverse and they're less pathogenic. And so this building had filtration. It did not have UVC. So moving along, when we think about building metrics, right now, so those of you who are listening, how do you monitor the performance of your building? So usually it's energy consumption. And now moving more to a hospital environment, we think about hospital profits. If you're designing an HVAC system for an operating room, you'll think about, is the surgical staff cool enough because they have layers of scrubs on? So we think about clinician comfort. But there's another metric that we really need to consider, which is kind of obvious, but it's understudied. And that metric is, if I can get it to switch, is, in the case of the hospital, the patient. In the case of an office building, that metric would be worker performance or absenteeism. In the case of a school, it would be student performance or absenteeism. But for the next little while, we're going to talk about the hospital environment and patient outcome. But please remember that what we're going to learn applies to occupants in all buildings, to a lesser or greater degree, but the same trends exist. So now we're going to have our first poll question, I think.
All right, first poll question.
Oops, whoa. First poll question.
I clicked it. There you go. Does your team monitor occupant health or performance? Please answer the question, one of the four answers. We follow ASHRAE guidelines. In-person meetings? We have a designated coordinator? Or not sure? I can see people start to answer here. Looks like maybe shaping up to be a 2-to-1 split with for every 2 that follow ASHRAE guidelines, there's one that's not sure. Perhaps we'll come back and review these again in a little bit. Looks like about 60-40 now, ASHRAE guidelines to not sure. Stephanie?
Okay, great. Boy, I wish I could talk to everybody, get real-time feedback, but so we did a study, we meaning myself and a group in the University of Chicago, did a study to ask how building indoor parameters affect patient outcomes. And specifically, we were looking at these new infections that people get from the hospital. They're called HAIs, or healthcare-associated infections. They used to be called nosocomial infections. These are things like MRSA, C. diff, bloodstream infections, ventilator-associated pneumonia, but the infections that you don't come in with but you get from the hospital. So we wanted to see if we could find any relationship between those infections in patients and the built environment. So we looked at 10 rooms, 5 on one floor and 5 on another floor. 5 of the rooms were oncology patients and 5 were your general med surge. So if you come in with appendicitis or you break your leg badly and you have to be in the hospital, that would be a general med surge. It was a brand new hospital when we started the study. It was LEED Silver, had about 270 patient beds, 24 ORs, had transplant units, beautiful facility. This drawing just shows 5 of the rooms. They're all single rooms. They all have vestibules, all pressurized. So we monitored those rooms for 13 months. We had data points from about every half an hour. We followed CO2 levels, lighting, like lux, lumens, temperature, hand hygiene with a video and an infrared beam breaker. We had room air changes, room traffic, indoor and outdoor relative humidity and absolute humidity, outdoor air fractions, and room pressurization. So we had about 8 million environmental data points. And we looked at, we correlated those data points with patient clinical outcomes, and again, specifically infections. And we had about 200 patients. So I hope that's clear. So we looked at the room, the patient room, in parameters, and used statistical analysis to apply that to see if there were correlations to the patient outcomes. So we were astounded by our results. As a matter of fact, we didn't really believe it. We sent the data to another statistician. What we found was this variable, the indoor variable that was the most statistically significantly related to patient infections, new infections, was indoor relative humidity. Not absolute humidity, but relative humidity. And as you can see on the bottom, on the x-axis, all the way on the left, it starts in the winter, goes through the summer, and back to the next winter. And the red columns are the number of healthcare-associated infections during those months. And the blue line is the average of the relative humidity of all 10 rooms, and they were all very closely related. So I don't know if anyone is surprised by this who hasn't seen this, but we were startled. So clearly, as the relative humidity approached 42%, the patient infections fell dramatically. And it was statistically significant to 0.02, p less than 0.02. So now we have another question.
And here it is. Does your facility monitor and regulate RH, relative humidity? One of these 4. Yes, we follow ASHRAE guidelines. No, the only good humidifier is one that is shut off. We have humid outdoor air most of the year, so we don't worry about it, or not sure. And I know living here in Oregon, where it rains 9 or 10 months out of the year, oftentimes people think, hey, it's wet out all the time. But when you bring that air inside and warm it up, it's below 40%. So the early results look like about 60% again follow the ASHRAE guidelines. A solid 10% shuts their humidifiers off, and about 1/7 has moist air in their locale, so they don't worry about it, and about 1/5 of the people are not sure. So about half follow, and the other half one of the others. So maybe about 50-50. And Steph, I'll toss it back to you.
Okay, great. So now we'll talk about indoor air hydration. And again, I like to stay away from the word humidification because for many of us, that word has bad connotations. We immediately think of 80% humidity. We think of mosquitoes, itchiness, body odor, mold. So I'm using the word air hydration or indoor air hydration to refer to the healthy range that will delineate as we move forward in this presentation. So we're going to talk about indoor air hydration, its effect on occupants, and so in the case of a hospital, that would be primarily patients and clinicians. But again, depending on your building, the occupant's going to be different. And then we're going to talk about the effects of indoor air moisture or hydration on microbes and on the microbes that cause disease, which are pathogens. So let's start with humans. Dry air is not good for people. I don't know how many of you go on airplanes very often, but if you do, like right now, I have a cold from flying. Many of us get sick, we get sinusitis, we get a cold, our eyes might get dry, our lips will be dry, our cuticles will be dry. Indoor air is really hard on people. Why is that? Well, we're about 85% water, 75 to 85%. Our brain's 85%. We need water for everything that we do. We need water to digest food, to breathe, to exchange oxygen and carbon dioxide. We need water to keep our structure intact, and we need water so that our immune system can be trained appropriately to fight infections and yet not be allergic to every single thing. So water is critical. So how much of our body actually is exposed to ambient air? So, for example, I'm a 50-kilogram woman. How much of me, in, say, square feet, is actually exchanging moisture with the room? So most of us might think, or many of us might think, okay, well, if you're fully clothed, that means your face, so maybe, I don't know, 12 square inches. But when you think about it, it's not only your skin that's exchanging moisture. It's your nose, your throat, your nasopharynx, all of your bronchial tubes, all the way down into the alveoli deep in your lungs where gas exchange occurs. So if you put all of those surfaces together, you end up with somebody, again, 50-kilogram person, it's about half of a tennis court with doubles, the double lines. It's about half of a tennis court that is actually exchanging air. So if you're in a room with, say, 20% relative humidity and you have a nice, well-hydrated human being, it's like putting a wet sponge in a dry room. The room air is going to suck water out of the person. So what does that do to us? Well, dry indoor air, when I say dry, I'm meaning less than 40%, which is most of our buildings, is very hard on us. Even mild dehydration to 1% is difficult. So the average person sitting in a room of relative humidity 20% becomes clinically dehydrated in 8 hours. And at that point, you're not even thirsty yet. Your urine has not even begun to darken, but you're still about 1% dehydrated. This impacts your eyes. It impacts your skin, the epithelial layer. It decreases wound healing. It has effects on your brain and your ability to think and concentrate. It causes increased blood viscosity and increased blood clotting, and you're at risk for more infections and more allergies. Let's start with the brain and cognition. Whoops. I'm just waiting for the slide to switch. The military is actually really interested in this and have done quite a few studies with even mild dehydration. My slide's not moving. Okay. Somebody else might want to take over here for a sec. Tom, I'm going to hand it over to you for a minute.
Okay, very good. Thank you, Stephanie. And so the slide that's showing right now shows the human brain. And from what I gather from Stephanie, they actually have imaging today that can show the difference in the size of your brain, one being dehydrated on the left and the other fully hydrated on the right.
Okay. Hey, Tom, thanks. I'm back.
Yeah, sure.
Thank you. Yeah, so this is a study, a 28-year-old man who is in a room at 30% relative humidity on the left. This study was done over about 20 hours with no hydration during this period. And you can see that the volume of the person's brain is significantly decreased. You can see how the brain is sort of pulled away from the skull. And you can also see in the little red circle, which is an enlargement, you can see that the neurotransmitter activity is greatly diminished in that slightly dehydrated brain. And then on the right, you have the same person who's been in 50% relative humidity, and you can see the brain is well hydrated, the neurotransmitter activity is very robust, which is what you want. So dehydration is also very hard on our skin. And clearly we need our skin for wound healing. We need it for keeping the outside out of us and the inside inside of us, which is basically teaching us what's to be allergic to and what not to be allergic to. We need our skin to protect us from injuries, to protect us from infections, and to preserve our internal water levels. So when your when your skin is well hydrated, like on the left, on the top, well hydrated, you can see a hair coming up. The yellow part is the epidermis. The deeper layers is the dermis. And the blue lines show that when you're well hydrated, you actually do not continue to lose water to the outdoor environment. The sort of oily skin layer keeps moisture where it should be. And underneath the drawing, you can see a biopsy with a nice intact epithelium, healthy dermis. And then on the right, where the skin is dehydrated, you can see that the epidermis is pulled apart. There are more cracks in the skin. More water is able to leave the body. And interestingly, in the picture underneath, in the microscopic picture, you see that not only is there skin flaking, but take a look at those little dark dots that are kind of coming up to the second layer. So if you think about what those dark dots are, you might be wondering. It's not dirt. Those are actually the nuclei of inflammatory cells. So without even your skin being symptomatic, it's not red, it's not itchy, you're already having inflammatory cells coming up to begin to combat some of the outside proteins and other things that are getting into the superficial layers of your skin. So when your skin is dry, you're much more prone to inflammation. What about our respiratory tract? So all of us from about our throats down deep into our lungs have a layer of mucus along our respiratory tract. And in that mucus are little hairs called cilia that are constantly washing upwards. And the cilia keep particles from going into our mouth and settling down into our lungs, because our lungs are very vulnerable. Once things get down into the alveoli, the gas exchange places, there's only one cell membrane that separates that airspace from our blood. And if a bacteria crosses into the blood, you can get sepsis, which is not something you want. So when the air is dry, we're inhaling that dry air, the mucus that lines our respiratory tract becomes more viscous. The cilia can't work as well, and inflammatory cells can't travel to combat any early invaders. So dry air is really hard on a respiratory tract. What about our eyes? So, our corneas are also in contact with the air. This is a study done in Australia with flights over 6 hours. So when the pilot takes off, in this case it was a guy, his vision is 20/20. But 6 hours later, his vision, even though the shape of his eyeball hasn't changed, his focus has deteriorated to 20/60%. So thankfully we have autopilots, so I don't have to show a bad landing. But dry indoor air is hard on our eyes. So this, I don't know, this video just is a laser video. Whoops. Slide should show, oopsies, a video of a person coughing. I don't think I'll be able to show the whole thing, but when you cough, particles come out at about 85 miles an hour. Some of them are larger than others. So what are the different determinants of whether that will infect somebody else who's standing a distance away? Well, a lot of how far those droplets travel will depend on how humid the air is. So unlike humans, pathogens, which are the microbes that cause disease, they love dry air. They travel further. Many are more infectious when they're in dry air. And not only are they more infectious, but little droplets that are in the air can settle on previously cleaned surfaces. They can be resuspended up into the air again, and they can travel great distances and for long periods of time. So let's just take a look at those different dynamics. So when I'm talking and you guys are all breathing, the droplets coming out of your mouth and nose are about 100 microns in diameter. And depending on how dry the air is, those droplets are going to shrink to reach equilibrium. So in dry air, meaning 20%, you'll quickly reach about a 0.5 micron diameter, which is known as a droplet nuclei. And those droplet nuclei can float for a long time, and they can go great distances. So that's transmission. Now let's talk about infectivity. This graph is showing a study done with guinea pigs in influenza A. And on the x-axis down at the bottom, you can see relative humidity going from 0 to 80. And then on the y-axis, you see virus viability, which is basically like infectivity. And from about 5% all the way into the green area, you can see that those viral particles are very infectious. And then around 40% relative humidity, you can see that the viability or infectivity drops dramatically, which is amazing. And then in some viruses and bacteria, the infectivity goes back up after 60%. It doesn't in this case. But there's a sweet spot between 40 and 60% relative humidity where humans are protected and pathogens are disabled, so to speak. So kind of to put some of these things together, if you're a patient in a hospital and somebody comes in to visit and they sneeze or cough in your room and it's dry, excuse me, the pathogen will circulate through the system. Tom, can you take over?
Sure. And so we have these different vehicles or means for which the infectious droplet is kept in play. So first you have the person who coughs it up, and then you have the ventilation system that takes up that and passes it throughout the entire system, recirculates it through the return air system and back into the supply. And then these particles are also allowed, again, when it's dry air, to recontaminate hands and surfaces. I also would like to, on an intuitive level, convey that we all know what it's like when it's very low humidity. Our shoes cause sparks on the carpet, or we get a spark at the doorknob. It's not too hard to imagine these tiny, tiny particles, a half a micron in diameter, being suspended by these relatively strong electrical charges. And so it may well be that these charges tend to keep the particles suspended in the air much longer than they would have been normally when you have humidity above 40%.
Thanks, Tom.
All right, you bet.
So this is Stephanie Taylor. I'm in a very dry room.
Mm-hmm.
The static electricity from my fingers is wreaking havoc on the tracking pad. So this slide just shows that. Let's move to a slightly different scenario, but this is really interesting. There's a belt in Africa called the meningitis belt, where when the dry weather comes in, there are devastating outbreaks of meningitis, which is a bacterial disease. And the epidemics are so predictable in comparison with this dry weather that they actually send in medical supplies when they see this sort of forecast. So you can see in the lower left, the graph shows that when the relative humidity drops, the disease mortality rate goes up. And the literature says once the humidity exceeds 40%, the epidemic ends. So there is something really amazing about that 40 to 60% indoor relative humidity range that's very protective for humans, and it decreases the pathogenicity of bad microbes. And it also looks like, going back to that microbiome diversity concept, that dry indoor air selects for certain pathogens, and a more hydrated indoor environment allows a more diverse microbiome to exist. So what should we be doing? Hopefully a lot of listeners are familiar with this Stirling diagram. So this shows on the bottom the relative humidity. The black areas are bad. Black's bad. On the left you have bacteria, viruses, just sort of respiratory infections, rhinitis, and ozone. And then over on the right you again have bacteria, viruses, mold, mites, allergies, and chemical reactions. And you can see in the middle, in the pink area, between 40 and 60% you have this sweet spot that's great for people. So this chart actually goes back to 1985. This was done for ASHRAE by Sterling, Avondale, and Sterling. So we do know this, but the way we're managing our buildings doesn't follow the studies that yielded that data. Most of our buildings in winter are more around that yellow zone. We'd like it to be right around the green zone, but even if we could aim for 45%, that would be great. So it seems like, okay, so now let's move to the sort of current attitudes about indoor humidification or indoor air hydration. There's sort of a raging battle going on. Building scientists, engineers, many HVAC designers, Tom not included, feels like if you want to protect the building, the drier the better. So there's no such thing as like too dry a building. And those of us who think about occupant health and productivity think we need indoor air hydration to protect the occupants. And again, that 40 to 60% range is very good for people, decreases infections, fewer allergies, improved overall hydration, improved wound healing if you're in a hospital, and increased work performance. But this is the push-pull that is going on.
And Stephanie, I'd like to interject here too that on your last slide you rightly had current climate around humidity. I want to point out that the technologies are changing and improving. We have more choices now for methods, for innovative methods of humidification than we've ever had. We see that ASHRAE Standard 190 pertaining to the air systems in hospitals, I'd say is being challenged.
Wait, 170. 170.
Thank you, 170. And so we're going to be seeing some new standards. And also I want to point out it's being recognized that with humans, and humans are by far the most important, but that equipment, supplies, and shelf life of medical supplies are all affected by humidity too. And so we've seen new standards requiring satellite storage rooms, now requiring humidification. Why? Because the shelf life is longer and it preserves the integrity of the product. Take it away, Steph.
Great. So many of you might be, if you're not multitasking, if you're still listening, you might think, okay, great, but building owners, they're not going to want to spend more money. So how do we relate this, I won't even call it an argument, how do we relate the benefits of indoor air hydration to building owners? Well, clearly we need to talk about the return on investment. So that hospital where we did the study, 250 beds occupied, 270-bed hospital, 85% occupancy, lost a lot of money from those infections. Over on the left, you see a list of 6 things: urinary tract infections, surgical wound infections, bloodstream sepsis, ventilator pneumonia, MRSA, and C. diff. Those are the 6 most common infections that people get from the hospital. And you can see in the red circle, in 1 year, that hospital lost $15 million, over $15 million in direct and indirect medical care costs. And now that's not reimbursable. They also tied up 11,000 of their patient bed days with patients for whom they could not be reimbursed. So that has a huge hit on a hospital's bottom line. And that doesn't even address litigation and issues that we really don't hear about, and they're hard to research.
Mm-hmm.
So here, this is hard to read, which is, I know, a big no-no, but this is just showing an ROI of decreasing healthcare-associated infections by 20%, which is very reasonable given what we found from the study, where infections went all the way down almost to 0. But this is a calculation of that hospital and the ROI on putting in a pretty expensive system. It calculates the downtime for the operating rooms and the facility. And so this is a very conservative ROI. And even given that it's conservative, you still have a 500% return on investment in the first quarter. So if you can get some of these metrics on the table, if you can understand what a hospital's infection rate truly is, or if we could begin to measure others' human well-being, healthy, and performance metrics, we could demonstrate a very clear benefit from properly hydrating the air. Okay, so Tom, you're on.
Very good, Stephanie. And so you have made a very compelling case that 40% humidity in a healthcare facility is highly desirable, and so now steps in the guardian, the engineer. And so how do we achieve 40% relative humidity in your facility? Well, it's my belief the first step is scientific method, and that means you make a plan, you do the plan, you see that it works or it doesn't work, you make a new plan, you do the plan, you never stop. So first of all, you have to know what your RH is now and have an accurate and repeatable method of measuring relative humidity. I've been to facilities where they have relative humidity sensors all over the place, and they never agree with each other. Well, they never calibrated, and they don't have something that they calibrated against. So first of all, you have to take measurements. You have to know what your humidity levels are. And then you need to identify key locations to do that. Obviously, there's places like operating rooms and so on. We talked about sterile storage. Steffi and I discussed that most hospitals don't measure patient rooms proper. Maybe 1 in 10, maybe 1 in 100. But those are your first steps. Let's know how to measure it accurately and systematically. Okay, now that you know how to measure it and you know you're short on it, you really have 2 choices if you're going to make humid air. And one way is to boil water. We use a heat source and we boil water. I show a tea kettle on this. It's a glorified tea kettle. You would pipe that steam to the space that you need it. I will point out that if you use a heat source type, if you're using an isothermal humidifier, what comes out of it is pure, sterile steam. And that's hard to beat, pure, sterile steam. The other system that's frequently used, and not so much in hospitals, is introducing liquid water into the air and letting the heat in the air itself evaporate the water. I show here a spray system and also an evaporative media system. The one in the lower left would be a wet medium that we pass air over to make the air moist. So just taking a quick look at some of the choices you have for boiling water. Many hospitals use a main boiler, and that steam is piped throughout the building, usually to air handlers to distribute the steam. It's least expensive because you have huge economies of scale of buying fuel oil and that sort of thing. Now, that's very common, although there is a little bit of a concern with chemicals that may be used in mitigating minerals in the boiler. They all use boiler chemicals. Some may get in the air, although it has not been clearly demonstrated. One of the single most common ones is an electric canister style. You'll see the hands touching a plastic cylinder there on the right. That's a boiling chamber. It's a tea kettle. This is a plastic one. It's electric, so it's really expensive to use energy-wise, but they're very easy to use and they cost the least to buy, so they're very, very popular. And you have the steam to steam, where some people are concerned about the central boiler systems. This is where we'd use steam to make clean steam with no chemicals. Again, it's a low cost of use, but you do have to buy an additional heat exchanger. And lastly, for middle-sized jobs to big jobs, they have gas-fired. Again, it's a tea kettle with a big gas burner under it. And they're expensive to buy at first, but in the long term, they're very low cost to use. So these are our choices when we're boiling water. And next we'll go on to the adiabatics. This is liquid water into the air. And you can see from my picture there again, we're spraying water under very high pressure directly into the air. There's an offering also where we use air itself as a compressed air to blow the water into the air. That's your second choice. And it's a bit more expensive to use than the first because it consumes air. And you'll note both of these use DI or reverse osmosis water, and that's so we're not introducing minerals into the air. Another popular choice, and I showed one on the previous page, you'd recognize as a swamp cooler. And I say, by the way, we dislike this term because the swamp coolers we use are very sophisticated. They may have polyester mediums. They may have stainless steel housings. They'll have ultraviolet lamps and perhaps even chemical dosing to make it very, very sanitary. So no, it's not using duck pond water to cool your space. Another technology is a piezoelectric transducer that vibrates very rapidly in a puddle of water, and it shatters the water into the air. But it does make a dense cold fog that's hard to manage. Now you'll see in red here at the bottom, all of these adiabatic technologies have sanitation concerns. They're manageable, but they all have sanitation concerns. Why? Because it's cold water that may sit for a while, and it may grow bacteria. Now I say these are manageable ones. The company I represent has numerous techniques of silver ions, again, ultraviolet lamps, or other dosing, and they also have means of testing and proving the sanitation of these. I alluded to earlier that the industry is changing. Currently, all these technologies I do not believe are allowed in American hospitals, and we believe that will change in the not-too-distant future.
Actually, Tom, that has begun to change. There's an amendment for ASHRAE 170 and adiabatic. The adiabatic coolers can be used. Sloan Kettering has implemented them. So well, we do have some early adopters who are using adiabatic with hygienic technology in healthcare space.
You bet. And that's wonderful, because a sidebar on that is then you get the benefit of perhaps incredible economic savings. Again, boiling water requires you to put energy into it. When you're using these spray systems, sometimes it's hot weather. Sometimes you're trying to cool your building. So when you spray the water into the air, it not only achieves your humidification goals, but also cools the air so you don't have to run your building cooling system, which is an enormous savings. So very quickly here, we've made some wet air. Now what do we do with it? There are several ways we distribute the moisture. On line 1, you'll see a stainless steel grid where steam would come out all the holes on that. You'd have that in your duct, and down the duct it would go. I show a duct system there. So that would be a central means of distributing it through your building. Down below, you'll see 3 different means of distributing moisture. The one in the middle is a blower for blowing steam directly into a space. Say, for instance, in the MRI room, we use these very frequently, where it's a little humidifier with a little blower to make sure the humidity is right in the MRI room. The other 2 shown at left and right would adiabatic that blow moisture directly into the space at high pressure. So I'm going to wrap it up here. Now that you got your 40% RH, you're measuring accurately, you're using good technology to put the steam or the moisture into the space. Continue to monitor. I recommend you have a gold standard. As I said, I've been to businesses where they have lots of humidity sensors, but they never calibrate them, nor do they make sure they read the same when they're together. So be sure to calibrate frequently. Don't settle for measuring the supply air. It's not the space. And address spaces not meeting the 40% RH goal. We talked about the central steam systems. They're very popular in hospitals. They go through the central air handler, and it goes everywhere, but you may find, again, satellite storage, sterile storage. I mentioned the MRI. They may not be meeting the needs of those spaces, so you can buy small, like electric or another style to treat those areas. Keep your humidifiers in good working order, and then the engineer is pretty much done. It's time for the doctor to get back to the office.
Well, thank you, Tom. So thank you very much. This is myself and Tom hanging out near the water. And I hope you can, you understand now why, to a large extent, public health is in the hands of building engineers, mechanical engineers, anyone who helps design systems for indoor spaces or helps manage indoor spaces. By properly hydrating your air, we can overcome a lot of these chronic and acute diseases. And at least this gives us another tool in our toolbox in hospitals with infection control, but it also gives us another way to enhance student learning, student school attendance, office productivity, and stop these alarming health trends. So thank you all very much, and please ask a lot of questions.
Okay, thanks to both of you. Great presentation, really interesting stuff. We have a couple of questions and thoughts in, but we've got a few minutes to spare, so if now that you've seen the whole main presentation, if there's something you want to follow up about, just use that field there to submit a question, and we'll get to it. One attendee mentions a specific slide, the one showing toxic and healthy outdoor shows a range from 0.4 to 0.6, he says, if he remembers correctly, on the pathogenic Y scale. He's asking for some context. You know, what does this mean in terms of risk to health of occupants? Are all bathrooms with a 0.6 a health risk, or how? Just he's looking for some help to understand that number better.
Which slide is this?
I'm not positive. He mentions showing toxic, but possibly mechanical versus healthy outdoor.
Oh, right. Okay.
It's the phylogenetic one. Yeah.
Yeah,
Yep.
I don't have a number for it.
Here it is. I gotcha.
Yeah, so yeah, you can pull it back up.
Yep, that's it.
So what was the question again, Robert?
He's looking for some context in how to evaluate, you know, what is a 0.6 in the big scheme of things? Are all bathrooms with a 0.6 a health risk, or, you know, just he's looking for some perspective on the scale.
So so if that were up to 10, 100%, that would mean that the DNA sequencing of that organism was 100% related to known pathogens. So this graph is using the next generation sequencing, the metagenomics. So we can't say that the red dots are actually pathogenic organisms because we don't have the capacity to show that with this technique, but we can say that the organisms that are labeled as red, for example, were 60% related to known pathogens. And then down the blue ones, say down around, I don't know, 0.2 and lower, so they only had a 20% crossover genetically with known pathogens. So I hope that helps.
Okay.
Feel free to email me, and I can send you this reference, or you can look it up. It's Kimball et al. But I hope that clarifies things.
Yeah. Okay, we've got a few more questions in the last couple of minutes. One attendee asks, how susceptible to hard water are steam systems, and what do you recommend to deal with that?
Well, Greg, that's a really good question. They're very susceptible to hard water. You always have to manage the minerals. And so there are actually products that are designed to manage really nasty water. And there's products designed to handle ultra-pure water. And so when you ask what do you recommend to remove the minerals, well, the answer is if you're going to remove minerals, you're either going to do it through a softener system or like an RO or DI system. And so those are your choices. But there's nothing, people frequently call and say, hey, can I put a filter on my water line? No, you can't filter out the minerals. You either have to be RODI or something like softener, or they'll come out in the humidifier.
Okay. Mike, another one kind of looking for some context in the bigger picture, asking how does airflow rate impact health risk as opposed to temperature or humidity controls effect on health risk?
Does that mean like room air changes?
Yes.
I think so, yeah.
Yeah. So interestingly, we're doing some additional research on this next week, looking at airflow in ICUs. And if you think about Stokes' law, if particles settle out of the air more quickly than they're being resuspended, the net result will be they'll go to the ground. So when you have proper indoor air hydration, you can. Mike Schofield has shown that you can decrease room air changes by 10%, and you save 70% of your fan energy in doing so. So you still need to move the air, but you can turn down room air changes significantly with properly hydrated air.
Good. Okay. Let's see. We've got a question about maintenance. You mentioned that a lot of those, the risks that did exist were manageable for the category of humidifiers. And attendee asked specifically how is maintenance tend to go with adiabatic systems?
Well, they do vary greatly, but the maintenance oftentimes is in dealing with, again, minerals. And so if you're going to have a high-pressure spray system, it has to be RO or DI water. You're taking that all out ahead of time. Then your maintenance is mostly proving of sanitation and an occasional check. Not a lot there. The swamp cooler that we talked about earlier, that has things you have to check, in terms of buildup on the media, like if it was especially dirty, that would have to be replaced or cleaned. And then the water, you always have to look after the water in adiabatic systems to assure it's sanitary. But again, it's a lot of it is mineral, dealing with the minerals. So there you go.
Right. Okay. Thanks. And one more viewer was referring to an earlier slide, the one with the brains. This is your brain on dehydration, so to speak. Asking what was the period of time spent at 30% RH that resulted in that shrinkage on the slide?
20 hours.
20 hours. Yeah. Okay. Yeah, that's a striking image.
Yeah, we have the reference for that because often we get questions about that.
Okay, yeah, that's great. And then again, the viewers can fetch these slides, download them if they want to. And we're 59 minutes after the hour, so we have a couple more, but I'm sorry, we will pass those on to the presenters. And again, no, they both will welcome your emails if you want to follow up about anything specific, but that will be all the time we have for questions today. Please join me in thanking Stephanie Taylor and Tom Berger for their presentations, as well as our sponsor, Nortec, for making the event possible. If you have additional questions or comments, you can also click the Email Us button on the console, and we'll help you with anything we can as well. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments with these. And please visit esmagazine.com for the archive of this presentation if you want to watch it, or a colleague wants to register and watch it, as well as information about our upcoming events. We appreciate your time, and we hope you found this webinar to be a valuable experience. Thanks for joining us. Have a good day.
Thank you.